Close your eyes and imagine the world as it was 12,800 years ago. The Ice Age is ending. This period, which scientists call the Alarid Interstadial, was a time of remarkable warmth and abundance. For roughly 2,000 years, the world had been thawing, and the transformation was extraordinary. Forests had crept northward across landscapes that had been buried under ice for millennia, colonizing the bare gravel and clay left behind by the retreating glaciers. Rivers swollen with meltwater carved new channels through the emerging land, creating vast wetlands and marshes that teemed with waterfowl, fish, and amphibians. The animal life of this warming world was almost beyond imagining. The glaciers that have covered the northern half of North America for tens of thousands of years are finally retreating, melting back toward the poles, and the land they leave behind is rich and green and teeming with life. The woolly mammoths of North America were magnificent creatures, standing up to 13 feet tall at the shoulder and weighing as much as 12 tons, with enormous curved tusks that could reach 16 feet in length and thick coats of reddish-brown fur that protected them from the cold. They were not the lumbering, stupid beasts of popular imagination. They were intelligent, social animals that lived in family groups led by matriarchs, much like modern elephants, and they communicated with deep, rumbling calls that could travel for miles across the tundra. Alongside the mammoths lived the American mastodon, a shorter, stockier relative that preferred the forests and wetlands of the eastern half of the continent, browsing on leaves and twigs rather than the grasses that the mammoths favoured. Mammoths the size of buses walk through forests of spruce and pine. The largest of these sloths, Megatherium, could weigh up to 4 tons and stand 20 feet tall when it reared up on its hind legs, using its enormous curved claws to pull down branches that no other animal could reach. There were several species of ground sloth in North America, ranging from the massive Megatherium to smaller species the size of a large dog, and they had been a successful group for millions of years, surviving multiple ice ages and climate shifts, which makes their sudden disappearance at the onset of the Younger Dryas all the more remarkable. Giant ground sloths taller than a man strip leaves from trees with their massive claws. The predators of Pleistocene North America were terrifying beyond anything alive today. Smilodon fatalis, the saber-toothed cat, was roughly the size of a modern lion but far more powerfully built, with enormous canine teeth up to 7 inches long that it used to deliver devastating slashing bites to the throats of its prey. The American lion, Panthera atrox, was even larger than Smilodon, the biggest cat that ever lived in the Americas, standing 4 feet tall at the shoulder and weighing over 700 pounds. The dire wolf, larger and more robust than any modern wolf, hunted in packs that could bring down animals as large as bison and young mammoths. The short-faced bear, Arctodus, was the largest predatory mammal in North America, standing 6 feet tall at the shoulder on all fours and over 11 feet when it reared up on its hind legs, a nightmare of teeth and claws that could outrun a horse over short distances. These saber-toothed cats crouch in the tall grass, waiting to ambush prey that has no idea the world is about to change forever. Across North America, to understand who the Clovis people were and where they came from, we must journey back much further, to a landscape that no longer exists. Between roughly 16,000 and 10,000 years ago, during the peak of the last glacial maximum and its aftermath, much of the world's ocean water was locked up in ice sheets and glaciers, causing sea levels to drop by more than 100 meters. This exposed land bridges that normally lay beneath the waves, most dramatically in the Bering Strait, where a vast plain called Beringia connected present-day Siberia to present-day Alaska. Beringia was not a narrow strip of land, but a vast continent in its own right, stretching over 1,000 kilometers from north to south at its widest point, encompassing lands from the Arctic Ocean to the North Pacific. This land bridge was the gateway through which the first humans entered the Americas. The timing of this migration has been hotly debated among archaeologists, with evidence suggesting that people may have arrived as early as 15,000 to 20,000 years ago, and possibly even earlier. These were intrepid explorers, moving across unknown lands in pursuit of game, driven by the eternal human impulse to see what lies beyond the next horizon. They brought with them knowledge of working stone, of making fire, of surviving in harsh climates, and of hunting large game. As they spread through the ice-free corridor between the Laurentide and Cordilleran ice sheets, or along the Pacific coast in boats, They radiated outward into a new world that had never known human predators. By the time the Clovis culture emerged, these migrations were ancient history, separated from the Clovis people by at least 1,000 years, and probably much more. The Clovis did not invent human settlement in the Americas, but they did perfect the art of hunting the largest animals the continent had to offer, and they spread their distinctive culture faster and farther than any other culture in pre-Columbian North America. Now picture a very different landscape, thousands of kilometers away. Across the grasslands and tundra of Pleistocene Russia and Ukraine, where modern cities now stand, there existed a remarkable material culture built not from trees, but from the bones of the very animals the Clovis people hunted. The mammoth bone huts of Eastern Europe represent one of the most ingenious adaptations to Ice Age living ever developed. In a landscape almost devoid of trees, where the tundra stretched for endless horizons broken only by scattered shrubs and grasses, the builders of these huts found abundant raw material in the bones of the mammoths that roamed the grasslands. Archaeological sites in Ukraine, particularly around the Dnieper River, have revealed the remains of dozens of these structures, some dating back over 20,000 years. The huts were built by stacking mammoth bones into a framework, with the largest bones forming the basic structure. Mammoth tusks, some longer than a man is tall, were used to form arches and doorways. The skulls, massive and robust, were arranged in layers to form walls. Smaller bones filled gaps, and the entire structure was covered with hides and sod to create insulation against the bitter cold. A single hut might require the bones of 10 to 15 mammoths, representing an enormous investment of labour and coordination. The existence of these bone huts tells us something profound about Ice Age society. The construction of such structures required sustained effort, social cooperation, and the ability to work together toward a common goal. It suggests that Ice Age peoples were not merely surviving, but had developed complex social systems capable of organising large-scale projects. The mammoth bone huts of Ukraine, separated from the Clovis culture by thousands of years and thousands of kilometres, represent a parallel adaptation to the challenges of the Pleistocene, different in implementation but similar in ingenuity. And then, when we look at other continents, we find that the great megafaunal extinctions of the late Pleistocene were not limited to North America. They were a global phenomenon, though the timing and severity varied by region. In Australia, the extinctions occurred somewhat earlier, around 50,000 years ago, coinciding with the arrival of the first humans on that continent. Over a period of perhaps just a few thousand years, the Australian megafauna vanished. The enormous wombat-like diprotodons, some weighing as much as an African elephant, disappeared. The giant marsupial lion Thylacoleo carnifex, an apex predator with enormous claws and crushing bite force, was gone. The giant kangaroos, the massive short-necked giraffes found nowhere else on Earth, the enormous ground-dwelling emu-like birds, all of them vanished, leaving behind a continent that would have seemed almost empty of large animals to a time traveller from the Ice Age. Whether the extinction of Australia's megafauna was caused by human hunting, by climate change, or by some combination of the two remains hotly debated, but the speed of the extinctions and their correlation with human arrival suggests that overkill played at least some role. In Eurasia, by contrast, the extinctions were more gradual and less complete. The mammoths, which had ranged across Siberia and into Europe, survived in isolated populations longer than their American cousins, persisting on remote islands like Wrangel Island in the Arctic until as recently as 4,000 years ago, representing one of the most isolated populations of Ice Age megafauna. The woolly rhinoceros, another iconic Ice Age creature, disappeared gradually over several thousand years rather than in the sudden pulse that characterized the North American extinctions. The pattern in Europe was patchy, with some megafaunal species surviving much longer than others, and with regional variations in the timing and severity of extinctions. In South America, the extinctions tracked closely with those in North America, and several groups of megafauna, including giant ground sloths that had survived in South America long after their North American cousins were gone, disappeared around the same time as the Younger Dryas. The global pattern suggests that while human hunting may have stressed megafaunal populations, there was a global climate event of sufficient magnitude to trigger extinctions on multiple continents, an event that most climate patterns alone would be expected to produce a synchronized extinction signal across the globe. That event is the Younger Dryas. The Clovis people are named after a site near Clovis, New Mexico, where their distinctive spear points were first identified in 1929, but they were not a single tribe or nation in any modern sense. They were a widespread cultural tradition, a way of making tools and a way of living that spread across the continent with remarkable speed, appearing in the archaeological record roughly 13,400 years ago and vanishing roughly 12,800 years ago, a span of only about 600 years. During that brief window, the Clovis tradition became the most widespread archaeological culture in the Americas, and the people who carried it were among the most successful hunter-gatherers the world has ever known. The question of human settlement in the Americas before the Clovis culture remains one of the most contentious debates in American archaeology. For much of the 20th century, the Clovis first model dominated, arguing that the Clovis people, appearing roughly 13,400 years ago, represented the first human inhabitants of the Americas. This theory was appealing in its simplicity and had the weight of archaeological visibility behind it. Clovis points were easy to identify, they were widespread, and they were associated with megafaunal hunting in a way that seemed to make logical sense. But the Clovis first model began to crumble in 1976 with the discovery of the Monteverde site in southern Chile. At Monteverde, archaeologists found evidence of human occupation dating to at least 14,500 years ago and possibly to over 16,000 years ago, predating the earliest Clovis sites by over 1,000 years. The implications were profound. If humans were in South America over 1,000 years before the Clovis culture appeared in North America, then either Clovis was not the first culture in the Americas, or the ancestors of the pre-Clovis peoples who built Monteverde must have travelled through North America on their way south, leaving behind little or no archaeological trace. Monteverde itself was a remarkable site. It contained the remains of wooden structures, some with stone foundations, suggesting permanent or semi-permanent settlements. It contained wooden tools, stone tools, and evidence of gathering and processing plant foods. It showed that pre-Clovis peoples were not merely nomadic big-game hunters, but were diverse in their subsistence strategies, exploiting a wide range of plant and animal resources. Since Monteverde, other pre-Clovis sites have been identified and accepted by the mainstream archaeological community. The Bluefish Caves in Yukon Territory in Canada show possible evidence of human occupation dating to over 24,000 years ago. The Deborah L. Friedkin site in Texas shows a sequence of stone tools older than any known Clovis points. The Gault site in Texas has produced tools dating to over 15,000 years ago. At Paisley Caves in Oregon, ancient sandals and other artifacts have been radiocarbon dated to roughly 9,300 years ago, but the archaeological context suggests that human presence at the site may be much older. The pre-Clovis sites are more scattered and less obvious than Clovis sites, which may explain why they were overlooked for so long. The people who left behind these early sites appear to have been less reliant on megafaunal hunting than the Clovis culture, exploiting a broader range of food sources and using more diverse toolkits. Some researchers have suggested that the Clovis culture may represent a cultural replacement, with a new group arriving from Siberia around 13,000 years ago and displacing or absorbing pre-existing populations. Others argue for cultural continuity, with Clovis representing an evolution of earlier traditions. But regardless of the origin of the Clovis culture, the discovery of pre-Clovis sites has firmly established that humans were in the Americas well before 13,000 years ago. The timing of the Monteverde occupation, separated from the Younger Dryas onset by only a few centuries, or at most a millennium, is suggestive. These people who left behind evidence of sophisticated stone tools and constructed settlements were about to lose their world. Now, shifting our attention to the other side of the planet, we find some of the most striking evidence for the Younger Dryas impact hypothesis, not in North America but in the ancient Fertile Crescent. Abu Huraira, located in northern Syria along the Euphrates River, was an important Natufian settlement that shows continuous occupation from the end of the last ice age through the Younger Dryas period. The site is remarkable for its detailed stratigraphic record, layer upon layer of archaeological deposits that tell the story of human adaptation to climate change. In the layers that date to the Younger Dryas boundary, researchers found something extraordinary. Scattered throughout the sediment were numerous pieces of shocked quartz, mineral grains that have been fractured and transformed under the extreme pressures of a cosmic impact. The presence of shocked quartz at Abu Huraira is significant because it cannot be easily explained by ordinary geological processes. Shocked quartz forms only under conditions of extreme pressure and temperature, such as those that occur during a hypervelocity impact or perhaps during an intense volcanic explosion. But Abu Huraira is not near any volcanoes, and there is no evidence of recent volcanic activity in the region. The shocked quartz at Abu Huraira points not upward to the sky, but outward to the cosmos. The discovery of shocked quartz at Abu Huraira was accompanied by other impact markers, including charcoal-rich layers suggesting large fires and the same stratigraphic position as the black mat found at North American sites. The coincidence of these markers across two continents separated by an ocean is difficult to dismiss as mere chance. The impact hypothesis proponents argue that the evidence from Abu Huraira demonstrates that whatever caused the Younger Dryas was not a regional event but a global catastrophe. They lived in small bands, probably numbering a few dozen individuals each, and they moved across the landscape following the great herds of megafauna that were their primary prey. The mammoth hunts must have been extraordinary events combining courage, skill, and coordination. Hunters armed with spears tipped with Clovis points would stalk a mammoth for hours or days. Some researchers believe they drove mammoths into marshes where the heavy animals became mired, then closed in with killing blows. At the Lena Ranch site in Arizona, 13 mammoth remains were found alongside Clovis points. At Murray Springs, also in Arizona, a mammoth and bison were found with tools next to a hunter camp with fire hearths and butchered bones just yards away. These sites are frozen moments in time, snapshots of a way of life about to vanish. Their camps, identified by scatters of stone tools, animal bones and fire-cracked rock, have been found in nearly every state in the lower 48, from the forests of the East Coast to the deserts of the Southwest, from the Great Plains to the Pacific Coast. A people we call the Clovis culture are thriving. They're among the most successful hunters the continent has ever known. The Clovis spear point is one of the most beautiful and sophisticated stone tools ever created by human hands. Each point was carefully shaped from a piece of high-quality stone, usually chert, jasper, obsidian, or chalcedony, using a technique called percussion flaking that required extraordinary skill and precision. The finished points were typically 3 to 5 inches long, symmetrical, with razor-sharp edges and a distinctive channel or flute running from the base partway up each face. This flute served a practical purpose, allowing the point to be securely hafted to a wooden or bone foreshaft, but the precision required to create it without breaking the point suggests that the Clovis knappers were artisans of the highest order. Some archaeologists have estimated that it took years of practice to master the Clovis fluting technique, and the finest examples of Clovis points are so exquisitely made that they seem almost too beautiful to use, leading some researchers to suggest that the finest points may have served ceremonial or symbolic purposes rather than purely practical ones. The Clovis people also traded their stone over enormous distances, with raw materials sometimes found hundreds of miles from their geological sources, suggesting a network of social connections and exchange relationships that spanned the continent. Crafting elegant stone spear points with a distinctive fluted shape that allows them to bring down animals many times their size. They have spread across the entire continent in what appears to be an astonishingly short period of time, from the Atlantic coast to the Pacific, from the edges of the retreating glaciers to the Gulf of Mexico. Their camps are found everywhere, their distinctive spear points scattered across dozens of states, and the archaeological record suggests a people who are confident, adaptable, and flourishing. The climate is warming, the ice is melting, the future looks bright, and then, in what appears to be the span of a single human lifetime, everything falls apart. The mammoths vanish, the giant ground sloths vanish, the saber-toothed cats vanish, the dire wolves, the American lions, the short-faced bears, the giant beavers the size of black bears, the American cheetahs, the ancient horses, the camels that had evolved in North America millions of years before, all of them disappear from the fossil record in a geological instant. The scale of the megafaunal extinction in North America is almost incomprehensible. The continent lost every land animal weighing more than about 1,000 kilograms, and most of the species weighing more than 100 kilograms. The list of the lost reads like an inventory of a prehistoric zoo. The Columbian mammoth, the woolly mammoth, the American mastodon, the ground sloths in all their variety, the glyptodonts, armadillo-like creatures the size of Volkswagen Beetles, with armoured shells and spiked tails, the ancient bison, Bison antiquus, which was about 25% larger than the modern buffalo, the stag moose, an enormous deer with bizarre palmate antlers that combined features of modern moose and elk. The beautiful horse, the North American horse, which had evolved on this continent over millions of years and had spread to Asia and Europe via the Bering Land Bridge, only to go extinct in its homeland while its descendants survived abroad. The camel, which like the horse had originated in North America and crossed to the Old World, disappearing from the continent of its birth. The tapir, the peccary, the giant tortoise, the giant condor-like teratons with wingspans exceeding 16 feet, all gone, all of them, in what amounts to a single page in the geological record. 35 genera of large animals, gone. The Clovis people themselves vanish from the archaeological record. The disappearance of the Clovis culture from the archaeological record is one of the most striking features of the Younger Dryas boundary. One layer, Clovis points everywhere, sophisticated tools, evidence of large game hunting, signs of a thriving, confident people. The next layer, nothing. Or rather, something very different. The post-Clovis cultures that appear after the Younger Dryas onset use different tool technologies, the Folsom tradition, the Dalton tradition, and others that were clearly descended from Clovis but adapted to a profoundly different world. The transition from Clovis to Folsom is one of the most dramatic cultural shifts in the archaeological record. The Folsom people appeared roughly 12,500 years ago as clear cultural descendants of the Clovis, but their world was profoundly different. The megafauna were gone, and Folsom adapted by focusing on bison. Folsom points are masterpieces of stone tool technology, thinner and more finely flaked, with longer flutes sometimes extending the entire length of the point. But the Folsom world was diminished, with fewer sites, smaller camps, and restricted territories, suggesting a dramatically reduced human population struggling to adapt. The Folsom points that replaced Clovis points were smaller and more delicate, designed for hunting bison rather than mammoths, because the mammoths were gone. The toolkits became more diverse, with more emphasis on plant processing tools and fishing equipment, suggesting that people were exploiting a wider range of food sources because the megafauna they had depended on had vanished. The population appears to have crashed. Archaeological sites from the early Younger Dryas are far fewer and far more scattered than Clovis sites, suggesting that the human population of North America declined dramatically in the centuries following the onset. Their beautiful fluted spear points replaced by smaller, cruder tools made by people who seemed to be living a harder, more desperate life. And the climate, which had been warming steadily for thousands of years, suddenly and catastrophically reverses. Temperatures plunge, the glaciers begin to advance again. Winter returns with a vengeance to a world that thought winter was over. This is the Younger Dryas, one of the most mysterious and terrifying events in the history of our planet, and for decades scientists have been arguing about what caused it. The name Younger Dryas comes from a small white and yellow flower called Dryas octopetala, a tough little Arctic plant that thrives in cold conditions. When geologists drill into the layers of sediment at the bottom of European lakes, they can read the climate history of the continent like the pages of a book, and in the layers that date to roughly 12,800 years ago, they find a sudden explosion of Dryas pollen. The Dryas flower is a survivor, a tough little plant that can grow in the poorest soils and the harshest conditions, and its appearance in the pollen record is like a geological alarm bell, signalling that the climate has shifted dramatically toward cold. The Younger Dryas was actually the third and most severe of three cold snaps during the deglaciation period, preceded by the oldest Dryas and the older Dryas, each of which was marked by the same telltale increase in Dryas pollen. But neither of the earlier events was anything like the Younger Dryas in terms of severity, duration, or impact. The Younger Dryas lasted approximately 1,200 years, from roughly 12,800 to 11,600 years before present, and during that entire period, conditions in the northern hemisphere reverted to near glacial cold. Sea ice expanded across the North Atlantic. Glaciers that had been retreating for thousands of years advanced again, and in North America, the effects were devastating. Boreal forests that had been advancing northward retreated hundreds of miles southward, replaced by tundra and open grassland. The Great Lakes region was plunged back into near-Arctic conditions. In the American Southwest, pluvial lakes that had filled desert basins during the Ice Age shrank as precipitation shifted, and lush wetlands that supported megafauna and humans dried out and disappeared. The Younger Dryas transformed North America from a land of abundance into a land of scarcity, and human populations contracted dramatically, retreating to the most productive habitats and abandoning marginal areas. Snow lines dropped hundreds of meters in mountain ranges around the world, evidence that a cold-loving Arctic plant suddenly appeared in regions that had been warming for millennia. The flower gave its name to the event, and the event itself is one of the most dramatic climate reversals in the geological record. The numbers are staggering. In the span of perhaps a decade, and possibly as little as a single year, average temperatures in the northern hemisphere dropped by as much as 10 to 15 degrees Celsius. To put that in perspective, the difference between the peak of the last ice age and the warm period that preceded the Younger Dryas was about 5 to 6 degrees. The Younger Dryas cooling was 2 to 3 times more severe than that, and it happened not over thousands of years but over a period so short that a single human being could have witnessed the entire transition. The speed of the Younger Dryas onset was terrifying. Ice core records from Greenland show that the transition from warm Alarode conditions to full Younger Dryas cold happened in as little as 1 to 3 years. Not centuries, not decades, years. The ice cores preserve annual layers of snowfall like tree rings, and the chemical composition of each layer tells scientists what the temperature was in that year, and what the records show is a cliff, a nearly vertical drop in temperature that happened so fast it would have been unmistakable to anyone alive at the time. One year the world was warm. The next year, or perhaps the year after that, winter had returned with a ferocity that no living human had ever experienced. The growing seasons shortened dramatically. Plants that had colonized the newly deglaciated lands died back as the cold returned. Animal populations that had expanded during the warm period suddenly found themselves in a landscape that could no longer support them. Imagine being alive for that. Imagine growing up in a world where the winters were getting shorter and the summers were getting longer, where the rivers ran free and the hunting was good, and then watching as everything reversed. The summers grow cold, the snows come earlier and stay later. The rivers freeze solid and stay frozen for months longer than they used to. The animals that you and your ancestors have hunted for generations begin to disappear. First, the biggest ones, the mammoths and the mastodons, and then progressively smaller species, until the hunting grounds that sustained your people for thousands of years are empty and silent. That is what the Younger Dryas looked like from the ground, and the question of what caused it has consumed scientists for decades. The traditional explanation for the Younger Dryas focused on the collapse of an ice dam in North America. During the last ice age, the Laurentide ice sheet, which covered most of Canada and extended into the northern United States, was enormous, in some places more than 2 miles thick. As this ice sheet melted, it created vast lakes of meltwater along its southern edge, the largest of which was at its maximum extent. Lake Agassiz covered an area of roughly 440,000 square kilometres, stretching across what is now Manitoba, Saskatchewan, Ontario, Minnesota, and North Dakota. It was the largest lake in North America by a factor of 10, a vast inland sea of glacial meltwater, held in place only by the wall of ice to the north. The water was bitterly cold, barely above freezing, and the lake had no natural outlet to the ocean. It simply grew and grew as the ice sheet melted, rising higher and higher against the ice dam that contained it, building up an almost inconceivable volume of potential energy. When that dam finally failed, the consequences were beyond anything in modern human experience. Lake Agassiz, a body of fresh water larger than all the current Great Lakes combined. Lake Agassiz was dammed by the ice sheet itself, and the traditional theory holds that at some point around 12,800 years ago the ice dam failed catastrophically. To understand the scale of this flood, consider that the total volume of all 5 Great Lakes combined is approximately 22,700 cubic kilometres. The water released from Lake Agassiz may have been roughly equivalent to this entire volume, released not over centuries or millennia, but in a matter of weeks or months. The flood would have been the largest freshwater flood event in the history of the Holocene, dwarfing every recorded flood in human history by orders of magnitude. The wall of water would have carved new drainage channels across the landscape, scoured bedrock down to bare stone, transported boulders the size of houses, and delivered its cargo of ice-cold freshwater to the ocean, with enough force to physically displace the warm, salty surface water of the North Atlantic, releasing an almost unimaginable volume of cold freshwater into the North Atlantic Ocean. The volume of water released was staggering, Estimates range from 9,500 to 21,000 cubic kilometers of fresh water, enough to raise global sea levels measurably, and this massive pulse of cold freshwater is thought to have disrupted the Atlantic meridional overturning circulation. One of the most intriguing pieces of evidence supporting the impact hypothesis comes from Greenland ice cores, those remarkable cylinders of frozen time that preserve the atmospheric chemistry of tens of thousands of years of Earth history. Ice cores are drilled from glaciers and ice sheets, and they contain trapped air bubbles, mineral dust, volcanic ash, and other particles that were present in the atmosphere when the snow that formed them fell. By analysing the chemistry of the ice, scientists can reconstruct the composition of the atmosphere at any point in the past. In 1998, a team of researchers drilling in Greenland ice found something unexpected at the layer corresponding to the Younger Dryas boundary. They detected a sudden spike in platinum concentration, an anomaly in the abundance of this rare element that corresponded precisely to the Younger Dryas onset. Platinum is extraordinarily rare in the Earth's crust and in the atmosphere. It concentrates in the Earth's core, and the only significant way it reaches the surface is through cosmic sources, particularly through meteorite and cometary material. A spike in platinum at the Younger Dryas boundary, therefore, suggests an input of cosmic material to the atmosphere at that precise moment. The platinum anomaly discovered in Greenland ice cores has since been found in ice cores from Antarctica and in ice cores from other glaciers around the world. The consistency of this discovery across multiple independent ice cores from different locations is striking. It is difficult to imagine a non-cosmic source for a global spike in platinum at a specific moment in time. The concentration of platinum in the Younger Dryas layer is elevated by a factor of several hundred compared to baseline levels, a difference far too large to be easily dismissed as analytical error or sample contamination. While some scientists have questioned whether the platinum anomaly could have been produced by other mechanisms, such as volcanic activity or weathering of old rocks, the case for a cosmic source remains compelling. A cosmic object large enough to deposit significant platinum in the atmosphere would almost certainly have been an impact event of considerable magnitude. Now, we must ask, where did this impactor come from? The night sky above Pleistocene Earth was not merely a beautiful background, but a shooting gallery in which our planet moved as an unwilling target. The solar system is home to numerous cometary streams, swarms of icy debris fragments whose orbits bring them periodically near the Earth. The most famous of these is the Leonid meteor stream, source of spectacular meteor showers in November. But there exists another meteor stream, far more ancient and far more ominous, whose discovery has profound implications for the Younger Dryas impact hypothesis. This is the Taurid meteor stream, a complex of debris left behind by the breakup of a large comet, possibly in the 27th century before the Common Era, although some researchers date its formation to over 10,000 years ago. The Taurid stream is at least 20 times broader than the Leonid stream and far more complex in its structure. Rather than a single stream, it is more accurately described as a complex of several streams, with different orbital characteristics and different seasons of activity. Some fragments of the Taurid complex produce meteor showers in the spring, while others produce showers in the summer and fall. The parent body of the Taurid stream is believed to have been a massive comet, perhaps tens of kilometers across, that fragmented into thousands or millions of smaller pieces. Some of these fragments are probably still intact somewhere in the Taurid complex, invisible to our observations until one of them finds its way to intersect with Earth's orbit. The Taurid stream crosses Earth's orbit at 2 points, and our planet passes through regions of the stream twice a year, once in the spring and once in the autumn. Most of the time, the debris in the stream is spread thinly enough that our planet passes through it without significant impact. But periodically, we enter denser regions, and when that happens, the rate of meteor impacts increases dramatically. Some astronomers have speculated that the Younger Dryas impact may have come from the Taurid stream, a fragment of a proto-Taurid complex that struck the Earth and triggered the cascade of events that led to the Younger Dryas. If this is true, then the Younger Dryas was not a random unpredictable catastrophe, but rather an event that has the potential to occur again should Earth's orbit bring it back into contact with Taurid stream debris. The Atlantic Meridional Overturning Circulation, or AMOC, is one of the most important climate mechanisms on the planet. It works like an enormous heat pump, carrying warm, salty water from the tropics northward along the surface of the Atlantic, where it releases its heat into the atmosphere, warming the lands around it. As the water cools and becomes denser, it sinks to the bottom of the ocean and flows southward again, creating a continuous loop that transfers vast amounts of thermal energy from the equator toward the poles. This circulation is the reason that London, which sits at the same latitude as Labrador, has a mild climate while Labrador is buried in snow and ice. It is the reason that Western Europe is habitable at all at its latitude, and it is exquisitely sensitive to changes in the salinity of the North Atlantic surface water, because the sinking of the cold, dense water that drives the entire system depends on that water being salty enough to be heavier than the water beneath it. When a massive pulse of fresh water enters the North Atlantic, it dilutes the surface water, making it lighter, preventing it from sinking and effectively shutting down the entire conveyor belt. The great oceanic conveyor belt that carries warm water from the tropics northward and is responsible for keeping Europe and the eastern coast of North America far warmer than their latitudes would otherwise suggest. The shutdown of the ocean circulation would not have been gradual or subtle. Climate models suggest that once the freshwater pulse crossed a critical threshold, the conveyor belt would have collapsed within a matter of years, and the effects would have cascaded through the entire global climate system like dominoes falling. The North Atlantic would have cooled dramatically as the supply of tropical heat was cut off. Storm tracks would have shifted southward. The monsoons that water much of tropical Africa and Asia would have weakened or failed entirely. The intertropical convergence zone, the band of rainfall that circles the equator, would have shifted, bringing drought to some regions and flooding to others. When the conveyor belt shut down, the warm water stopped flowing north, and the northern hemisphere plunged back into near-glacial conditions. This explanation, known as the meltwater pulse hypothesis, was the dominant theory for decades, and it remains widely accepted in the scientific community. But it has problems. The timing does not perfectly match the geological evidence. The exact route of the meltwater drainage has been debated, with some scientists arguing it flowed through the St. Lawrence River to the Atlantic, others arguing it flowed north through the Mackenzie River to the Arctic Ocean, and still others suggesting it may have taken multiple routes at different times. And the meltwater pulse hypothesis does not easily explain some of the other things that happened at exactly the same time as the Younger Dryas onset, things that suggest something far more violent and far more sudden than a simple flood. In 2007, a team of scientists led by the paper was published in the Proceedings of the National Academy of Sciences and was signed by 26 authors from multiple institutions. The lead author, Richard Firestone of Lawrence Berkeley National Laboratory, published a paper that proposed a radically different explanation for the Younger Dryas. They called it the Younger Dryas Impact Hypothesis, and it suggested that approximately 12,800 years ago, a comet or a swarm of cometary fragments struck the Earth or exploded in the atmosphere above the Laurentide ice sheet, triggering a catastrophic chain of events that caused the Younger Dryas cooling, the megafaunal extinctions, and the disappearance of the Clovis culture. The evidence they presented was startling. Across North America, in a thin layer of sediment that dates to the exact onset of the Younger Dryas, they found a suite of materials that are associated with cosmic impacts. The nanodiamonds were found in a specific type called lonsdaleite, also known as hexagonal diamond, which forms under the extreme shock pressures that occur during hypervelocity impacts and is extremely rare in nature. The presence of lonsdaleite at Younger Dryas boundary sites was particularly significant because it is very difficult to explain through any mechanism other than a cosmic impact or an extraordinarily powerful explosion. The nanodiamonds were found embedded in carbon spherules, tiny balls of carbon that form when organic material is exposed to temperatures exceeding 2000 degrees Celsius, temperatures that are consistent with an impact fireball, but very difficult to achieve through any other natural process. They found nanodiamonds, microscopic diamonds that form under the extreme pressures and temperatures of an impact event. They found magnetic microspherules, tiny metallic beads that form when rock is melted and ejected into the atmosphere by an impact, cooling into spherical shapes as they fall back to Earth. They found elevated levels of iridium, an element that is rare on Earth's surface but common in asteroids and comets. They found carbon spherules, little balls of carbon that form in intense fires, and they found something called a black mat, a distinct dark layer in the geological record that marks the onset of the Younger Dryas, at sites across North America and beyond. The black mat itself is a remarkable phenomenon. It is a thin layer of dark, organic-rich sediment that was deposited across vast areas of North America at the onset of the Younger Dryas. Its darkness comes from a combination of charcoal from widespread fires, algal growth in newly formed wetlands, and organic matter that accumulated in the wetter, cooler conditions of the early Younger Dryas. The black mat has been identified at more than 70 sites across the continent, and its stratigraphic consistency is striking. At every site where it has been found, it occupies the same position in the geological record, separating the warm, dry sediments of the Alarud period below from the cold, wet sediments of the Younger Dryas above. The black mat is found at dozens of archaeological sites, and it is always in the same stratigraphic position, directly above the last Clovis artifacts and directly below the first post-Clovis artifacts. Below the black mat you find Clovis tools and megafaunal bones in abundance. Above it, both are gone. Let us examine in detail the markers of impact that scientists have discovered, for each one tells part of the story of what happened on that fateful night. The nanodiamonds, microscopic carbon structures formed under extreme pressure, are perhaps the most direct signature of a cosmic impact. These nanodiamonds are found embedded in carbon spherules, little balls of carbon that form when organic material is superheated to temperatures exceeding 2000 degrees Celsius. The temperature required for carbon spherule formation is extraordinarily high, and is difficult to achieve through any process other than an impact. In the laboratory, when researchers simulate impact conditions by firing projectiles at targets at extreme velocities, the resulting debris includes both nanodiamonds and carbon spherules, exactly as found in the Younger Dryas boundary layers. The presence of these materials in multiple independent samples from across North America and at sites around the world is a powerful indicator that something extraordinary happened at the Younger Dryas boundary. The magnetic microspherules are another compelling piece of evidence. These are tiny balls of metal, typically composed of iron and nickel, that form when rock or metal is melted by extreme heat, and then rapidly cools as the molten droplets fall through the atmosphere. They are extremely rare in nature under normal conditions, but they are abundantly produced during impact events and during certain types of volcanic activity. The microspherules found at Younger Dryas boundary sites have been analysed for their magnetic properties and their chemical composition. The results show that they are consistent with cosmic sources, with iron to nickel ratios similar to those found in meteorites. The charcoal layers that mark many Younger Dryas boundary sites are perhaps the most visible evidence of catastrophic fires. These are not thin layers of charcoal dust, but thick, concentrated deposits of burnt organic material, indicating fires so intense and so widespread that they generated enormous quantities of charcoal that was then buried by subsequent sediment. Some of these charcoal layers are so thick that they contain visible chunks of charred wood, suggesting that large pieces of biomass burned so completely that they were reduced to carbon. In some cases, the charcoal layers show evidence of having been deposited in water, suggesting that the charcoal was transported by water and then settled to the bottom of lakes or slow-moving rivers. This mixing of fire evidence with water evidence tells a story of simultaneous destruction by fire and flood, exactly what would be expected from an impact into the Laurentide ice sheet. The black mat itself, that thin dark layer found at over 70 sites across North America, is perhaps the most consistent marker of the Younger Dryas boundary. The black mat is composed of a mixture of materials, including charcoal from fires, pollen from early Younger Dryas vegetation, and organic material from soil. The blackness itself comes primarily from charcoal, but also from concentrated organic matter that accumulated as the early Younger Dryas climate became wetter and promoted algal growth. The black mat is almost always precisely at the boundary between the warm, dry Clovis age deposits below and the cold, wet post-Clovis deposits above. The consistency of this marker across so many sites suggests that something happened everywhere at the same moment, something that created conditions for charcoal deposition, for the establishment of wetlands and algal growth, and for the rapid change in vegetation and climate that characterizes the Younger Dryas. The combination of all these markers, nanodiamonds and carbon spherules, microspherules and shocked quartz, elevated platinum and iridium, thick charcoal layers and the black mat, all appearing in the same stratigraphic position, tells a story of cosmic catastrophe that is difficult to ignore. Each marker by itself might be disputed or explained through alternative mechanisms, but the combination of markers across multiple continents and multiple independent research sites presents a case that is increasingly compelling. The black mat appears to mark a boundary, a dividing line between the world before and the world after, and the impact hypothesis suggests that this boundary was created by a cosmic catastrophe. The impact hypothesis proposes that the comet or cometary fragments did not necessarily create a traditional impact crater. If the object or objects struck the Laurentide ice sheet, which was up to 2 miles thick in places, this is one of the most elegant and one of the most frustrating aspects of the impact hypothesis. If a large object struck a 2-mile thick ice sheet, the impact would have melted and vaporized cubic kilometers of ice instantaneously, creating a temporary crater in the ice that would have been quickly erased as the remaining ice flowed in to fill the void. The enormous heat of the impact would have converted vast quantities of ice directly into superheated steam, generating a blast of water vapor and ice fragments that would have been launched into the upper atmosphere at hypersonic velocities. The atmospheric effects would have been devastating. The water vapor, combined with the dust and debris from the impact, would have created a high-altitude cloud layer that could have persisted for months or years, reflecting sunlight back into space and contributing to rapid cooling. The ice fragments launched into the upper atmosphere would have fallen back to Earth over a wide area, potentially triggering secondary impacts and fires hundreds or thousands of miles from the primary impact site. The impact would have vaporized enormous volumes of ice without leaving a crater in the bedrock beneath. If the impactor was a comet or cometary fragment roughly 4 kilometers in diameter, as some researchers have estimated, the energy released upon impact would have been on the order of 10 million megatons of TNT, roughly 100,000 times more powerful than the largest nuclear weapon ever detonated. Even an airburst, in which the object exploded in the atmosphere before reaching the surface, could have released energy equivalent to thousands of nuclear weapons. Similar to but vastly more powerful than the Tunguska event, provides a chilling preview of what a larger impact could do. On the morning of June 30th, 1908, something exploded over the remote Siberian taiga with a force estimated at 10 to 15 megatons of TNT, roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The explosion flattened approximately 80 million trees across an area of over 2,000 square kilometers, and the shockwave was detected by seismographs around the world. If the same object had entered the atmosphere 4 hours and 47 minutes later, the rotation of the Earth would have placed Moscow directly beneath the blast zone, and the entire city would have been obliterated. The Tunguska object left no crater, consistent with an airburst, and this is precisely the kind of event that the Younger Dryas impact hypothesis proposes, but on a vastly larger scale. The Tunguska event of 1908, when a relatively small object exploded over Siberia and flattened 2,000 square kilometers of forest. The energy released would have been equivalent to millions of nuclear weapons, and the immediate effects would have been apocalyptic. The impact would have generated a massive shockwave that would have flattened forests and killed animals across a vast area. What was daily life like for the Clovis people in those final centuries before the world changed? Imagine yourself awakening in a Clovis camp in what is now the American Southwest, somewhere in Arizona or New Mexico, 600 years before the Younger Dryas. The camp sits on a low rise overlooking a river valley, chosen for its proximity to water, good views of approaching game, and defensible position. Your band consists of perhaps 30 people, men, women, and children, related by blood and marriage. The huts are simple structures, circular arrangements of posts driven into the ground and covered with hides and sod, leaving a central opening at the top for smoke from the fire. Inside it is dark and warm, insulated against the cold nights of the desert. You wake early before dawn to the sounds of the camp stirring. Children cry, dogs bark, people move quietly about their morning tasks. The fire at the center of the camp is kept burning constantly, fed with wood gathered in the previous day. The wood is precious in this semi-arid landscape, and gathering enough to keep fires burning is a constant task. Adults emerge from the huts carrying things. A woman carries baskets woven from willow branches, where she will gather the seeds of desert grasses, wild plants, and nuts that contribute substantially to the diet of the band. A man carries a hunting spear, its foreshaft newly attached with sinew, tipped with a beautifully fluted Clovis point that he crafted himself over weeks of careful work. The lithic toolkit of the Clovis people is extensive. Beyond the famous fluted points, Clovis hunters carried scrapers for processing hides, knives for butchering game, gravers for working bone and antler, microblades for fine work, and specialized tools whose exact purpose remains debated among archaeologists. The quality of the toolkit suggests that these were not primitive people, but skilled craftspeople who understood their materials and their tools intimately. The day's tasks are clear. The men will hunt, following the tracks of mammoths and bison they observed days earlier. The women will gather plants and small game, trapping rabbits with snares, capturing birds with nets and traps. The children will learn by watching, gradually acquiring the skills they will need to survive in a world of animals far larger than themselves. This sexual division of labour was not rigid, and women likely participated in hunts, while men participated in gathering, but there was a general tendency towards specialisation. The relationship between men and women in Clovis society remains mysterious, but skeletal remains sometimes show signs of great strength in both sexes, suggesting that life was physically demanding for everyone. The food in the camp is abundant. The Alarode interstadial provided ideal conditions for large animal populations. Mammoths and bison roamed in vast herds. The climate was warm, the vegetation was lush, and the hunters of the Clovis culture had adapted perfectly to exploit this abundance. There is meat, a staple of the Clovis diet, supplemented by gathered plant foods, nuts, and seeds. Water is available nearby. Life is good. These Clovis people cannot imagine what is coming. The world they inhabit seems stable and eternal. The hunting is good, the climate is reliable, and the future stretches ahead seemingly without limit. But somewhere above, unseen, the cosmos is moving in its eternal dance, and on one fateful night still centuries away, something is going to fall from the sky and change everything. Now let us turn our attention to the physics of what such an impact would do to the planet and the climate. The concept of nuclear winter emerged during the Cold War as scientists contemplated the consequences of a large-scale nuclear exchange. If thousands of nuclear weapons were detonated, the models showed that soot and dust would be lofted into the stratosphere, creating a pall so thick that sunlight would be blocked, temperatures would plummet, and the Earth would be plunged into darkness and cold that would persist for months or even years. The nuclear winter hypothesis was controversial at first, but the mechanisms behind it are sound. Large fires generate tremendous amounts of soot. Soot particles are small enough to remain suspended in the upper atmosphere for extended periods. These particles absorb and reflect sunlight, reducing the amount of solar radiation that reaches the surface. When enough soot accumulates, the cooling becomes significant and global in extent. An impact winter following the Younger Dryas impact would have operated through similar mechanisms. The impact itself would have generated tremendous heat, igniting vast wildfires across a continent or more. The fires themselves, burning forests, grasslands, and vegetation, would have generated enormous quantities of soot. The heat from the impact or the explosion in the atmosphere would have lofted this soot into the upper atmosphere, where it would have remained for weeks, months, or even years. The primary mechanism of cooling following an impact or cosmic event is not the darkness itself, though that is certainly part of the problem, but rather the disruption of the hydrological cycle. When soot blocks sunlight, the land and oceans cool, but more importantly the water cycle is disrupted. Less evaporation occurs, reducing rainfall. The cooling of the oceans alters currents and circulation patterns. The disruption cascades through the climate system, with impacts on weather patterns, monsoons, and seasonal cycles. An impact winter lasting just a few years would be sufficient to trigger a global climate shift of the magnitude of the Younger Dryas, especially if the impact occurred at a moment when the climate system was already sensitive to perturbations, as it was during the deglaciation, when the Laurentide ice sheet was melting and vast volumes of fresh water were entering the North Atlantic. The heat pulse from the impact would have ignited continent-wide wildfires, and the evidence for continent-wide wildfires at the Younger Dryas onset is substantial and disturbing. The charcoal record shows a spike in biomass burning that is one of the largest in the entire Pleistocene record, suggesting fires of extraordinary intensity and extent. At some sites, the charcoal layer is so thick and so concentrated that it implies a conflagration that consumed everything in its path: forests, grasslands, and the animals that lived in them. The fires would have generated enormous quantities of soot and ash that would have been carried into the upper atmosphere by the convective columns of the fires themselves, creating a pall of smoke that could have darkened the sky for weeks or months, reducing the amount of sunlight reaching the surface and amplifying the cooling effect of whatever had caused the initial temperature drop. There is evidence for exactly this in the form of a charcoal-rich layer found at Younger Dryas boundary sites across North America. The soot and ash from these fires would have been lofted into the upper atmosphere, blocking sunlight and triggering a period of global cooling, much as nuclear winter models predict for the aftermath of a nuclear war. The impact into the ice sheet would have released the waters of Lake Agassiz and other glacial lakes in a catastrophic flood that would have dwarfed anything previously imagined. The flood would have carried icebergs, debris, and unimaginable volumes of fresh water into the North Atlantic, disrupting the ocean circulation and triggering the climate reversal that defines the Younger Dryas. Across the southeastern United States, from New Jersey to Florida and westward to Texas, the landscape is dotted with thousands of mysterious elliptical depressions called the Carolina Bays. These features were first described in scientific literature in the early 20th century, and they have puzzled geologists ever since. The bays are remarkably uniform in shape, almost always elliptical, with their long axes aligned in a northeast to southwest direction. They range in size from a few hundred meters to over a kilometer in length, and they are typically surrounded by a rim of elevated sandy material. The origin of the Carolina Bays has been debated for decades. Some researchers argued that they were produced by wave action in an ancient Pleistocene lake. Others suggested they were created by meteoric impacts. Still others proposed they were wind-formed depressions. But in recent years, a compelling new hypothesis has emerged. If a swarm of cometary fragments struck the Earth or exploded in the atmosphere above the Laurentide ice sheet, some of the ejecta and secondary debris would have travelled southeastward, raining down on the southeastern United States with tremendous force. The impact of small meteorites moving at hypersonic velocities would create elliptical impact craters aligned perpendicular to the direction of travel of the incoming debris. The orientation of the Carolina Bays, their remarkable uniformity in shape, their concentration in a specific region, and their age all are consistent with this hypothesis. If the Carolina Bays are indeed impact craters from the Younger Dryas event, they represent a direct and visible record of cosmic bombardment written across the landscape of America. While the Carolina Bays hypothesis remains controversial, it has attracted the interest of serious researchers and has generated much discussion in the scientific community. Whether or not all of the Carolina Bays are impact features, their existence reminds us that cosmic events leave scars on the landscape that we are only beginning to learn to recognize. On the other side of the continent in Washington state, we find evidence of another catastrophic event that may be linked to the Younger Dryas impact. The channeled scablands are a vast region of eastern Washington, covering thousands of square kilometers, where the landscape bears the unmistakable marks of catastrophic flooding. The scablands consist of networks of channels, some of them over 100 meters deep, carved into basalt bedrock. The channels follow patterns that suggest they were created by flowing water, moving with tremendous force and volume. Between the channels, erosion has stripped away all topsoil and regolith, leaving bare bedrock or scattered blocks of stone. The landscape looks like it has been scoured by a giant hand, which is essentially what happened. The traditional explanation for the channeled scablands comes from J. Harlan Bretz, who in the 1920s proposed that the landscape had been carved by catastrophic floods released from glacial Lake Missoula, a vast lake created by meltwater from the Cordilleran ice sheet. Bretz's hypothesis was initially ridiculed because the scale of the proposed flood seemed impossible, but over time, as additional evidence accumulated, the scientific community accepted that Bretz was correct. Glacial Lake Missoula contained water equivalent to all of the water currently in the Great Lakes, and when ice dams holding back this water failed, the resulting floods were incomprehensibly vast. Multiple floods, each one perhaps as destructive as the one before, swept across eastern Washington, creating the channeled scablands. The most recent of the Missoula floods appears to have occurred around 13,000 years ago, which places it within or very near the Younger Dryas boundary. Some researchers have proposed that the Younger Dryas impact may have triggered or accelerated the failure of the ice dams holding back glacial Lake Missoula. The heat from an airburst or impact explosion could have weakened ice dams, or the shock of the impact could have destabilized ice that was already on the verge of failure. If this is true, then the catastrophic floods that carved the channeled scablands may represent not an independent catastrophe, but rather a secondary consequence of the cosmic impact. The scale of the flooding was almost incomprehensible. The floods moved at speeds of up to 100 kilometers per hour, carrying boulders the size of buildings, scoured bedrock down to bare stone, and transported unimaginable volumes of sediment and debris. A time traveller transported back to witness the floods would have seen landscape transformation occurring at a pace visible within hours and days, the face of the Earth literally changing before their eyes. And the impact may have destabilised the ice sheet itself, causing portions of it to surge and advance, contributing to the reglaciation that followed. The impact hypothesis remains controversial. Many scientists accept the meltwater pulse hypothesis and argue that the evidence for an impact is not conclusive. They point out that nanodiamonds can form through processes other than cosmic impacts, that the distribution of the supposed impact markers is inconsistent, and that no definitive impact crater has been identified. The intensity of the scientific debate over the Younger Dryas impact hypothesis reflects the enormity of what is at stake. If the hypothesis is correct, it means that a cosmic catastrophe fundamentally altered the course of human history, that the world we live in today is the product of an event that came within a hair's breadth of ending human civilization before it began. The debate over the Younger Dryas impact hypothesis has intensified in the early 2020s as additional evidence has accumulated. In 2022, a major international research effort published findings suggesting that the platinum anomaly previously discovered in Greenland ice was far more widespread than originally believed. Samples from over 100 locations across the globe showed evidence of elevated platinum levels at the Younger Dryas boundary, a global signal that is extremely difficult to explain through any mechanism other than extraterrestrial input. Furthermore, new analyses of ice cores have revealed not just platinum spikes, but anomalies in iridium concentrations as well. Iridium is another element that is extraordinarily rare in the Earth's crust, but common in meteoritic and cometary material. The simultaneous spike in both platinum and iridium in samples from multiple independent ice cores is a powerful signal of cosmic origin. In 2023, studies using advanced analytical techniques identified microspherules embedded within the platinum-rich layers in ice cores. These microspherules have chemical compositions consistent with melted cosmic material, containing high levels of nickel, iron, and other elements common in asteroids and comets. The microspherules are tiny in the micrometer size range, but their presence is significant because they indicate that at the moment the platinum was deposited, there was also significant amounts of pulverized cosmic material entering the atmosphere. These findings have gradually shifted the perception of the impact hypothesis within the scientific community. What was once a fringe idea is increasingly accepted as plausible, and many researchers now treat it not as a speculative hypothesis, but as a serious explanation that must be considered alongside other mechanisms in explaining the Younger Dryas. The accumulation of evidence has been particularly striking because the markers of impact, the platinum anomalies, the nanodiamonds, the microspherules, and the charcoal layers all appear in the same stratigraphic position across multiple continents and across multiple independent research sites. In the language of geology and paleontology, the consistency of markers across widely separated locations is one of the strongest pieces of evidence that something truly global happened at a specific moment in time. The pattern cannot easily be dismissed as local contamination or misidentification. Ice cores preserve annual and seasonal layers that can be counted and dated with extraordinary precision. The Greenland Ice Core Project, or GRIP, has produced an ice core that extends back over 100,000 years, with individual layers representing single years of snowfall. By counting the layers, scientists can determine the age of any layer with a precision of plus or minus a few decades for material dating to the Younger Dryas. The oxygen isotope ratios in the ice tell us the temperature in the year that snow fell. The trapped air bubbles tell us the composition of the atmosphere. The dust particles and aerosols trapped in the ice tell us whether there was volcanic activity, whether there were large fires, and whether there was dust in the atmosphere. When researchers examine the ice cores through the Younger Dryas boundary, the story they tell is remarkable. Below the boundary, the oxygen isotopes show a relatively stable warm climate, similar to present-day conditions. Above the boundary, the oxygen isotopes show a sudden and dramatic shift to much colder conditions. The shift is so abrupt that it is visible as a clear line in the ice when you slice the core lengthwise and examine the isotopic signatures. There is no gradual transition over decades or centuries. The change is essentially instantaneous on geological timescales, occurring within years, and it is at precisely this boundary layer that the platinum anomalies appear, along with the microspherules, the nanodiamonds, and the charcoal-rich material indicating large fires. The opponents of the hypothesis have published numerous papers challenging the evidence, arguing that the nanodiamonds may have been contamination, that the magnetic microspherules could have been produced by ordinary fires or volcanic activity, that the timing of the supposed impact does not precisely match the onset of the Younger Dryas at all sites. The proponents have responded with additional evidence, new sites, new analyses, and new data that they say support the impact interpretation. The debate has played out across dozens of scientific journals, at conferences around the world, and occasionally in the popular press, and it shows no signs of being resolved anytime soon. But the accumulation of evidence over the past 15 years has shifted the scientific conversation. What was once considered a fringe hypothesis is now taken seriously by a growing number of researchers, and the question has evolved from whether a cosmic event occurred to exactly what kind of event it was and how it interacted with other forces to produce the Younger Dryas. The debate has been fierce, sometimes bitter, and it continues to this day. But the evidence for the impact hypothesis has grown stronger over time, not weaker. In 2012, a team of scientists identified what they believed to be a large impact crater beneath the Hiawatha Glacier in northwestern Greenland. The discovery was made using airborne ice-penetrating radar, which revealed a circular depression beneath nearly a kilometre of glacial ice. The structure had all the hallmarks of an impact crater, including a raised rim, a central peak, and the characteristic bowl shape produced by hypervelocity impacts. When the discovery was announced in 2018, it generated enormous excitement in the scientific community because it appeared to provide the smoking gun that the impact hypothesis had been missing, a physical crater that could be linked to the Younger Dryas event. Samples of glacially transported sand and rock from beneath the ice contained shocked quartz grains and other impact indicators, strengthening the case that the structure was indeed an impact crater, a structure roughly 31 kilometers in diameter that appeared to be relatively recent in geological terms. While the dating of the Hiawatha crater is still debated, and some scientists believe it may be older than the Younger Dryas, its discovery demonstrated that large impacts can indeed be hidden beneath ice sheets, exactly as the impact hypothesis predicted. Additional impact markers have been found at sites around the world, including in Europe, the Middle East, and South America, suggesting that whatever happened at the onset of the Younger Dryas was not merely a North American event, but the Younger Dryas was not limited to North America. Its effects were felt around the world, although the severity varied by region. In Europe, temperatures plunged, and the forests that had been advancing northward retreated, replaced by the Arctic tundra vegetation that gives the event its name. The effects of the Younger Dryas on human cultures worldwide provide compelling evidence for its catastrophic nature. The Natufian culture of the Levant, which had been developing some of the earliest experiments with settled village life and plant cultivation, was disrupted by the cold and drought of the Younger Dryas, and many Natufian settlements were abandoned as people reverted to a more mobile nomadic lifestyle. In South America, the Younger Dryas coincided with the extinction of several megafaunal species and significant changes in human settlement patterns. In Africa, lake levels dropped dramatically as rainfall decreased, and the Sahara, which had been relatively green and habitable during the warm period, began to dry out. Even in the southern hemisphere, where the Younger Dryas cooling was less severe, there is evidence of significant climate disruption, including changes in ocean circulation, shifts in rainfall patterns, and alterations in vegetation. The global nature of the event is one of the strongest arguments for a catastrophic cause, because a simple meltwater pulse in the North Atlantic would not be expected to produce simultaneous effects on the other side of the planet. A global catastrophe. The megafaunal extinction that coincides with the Younger Dryas is one of the great mysteries of paleontology. In the span of roughly 1,000 years centered on the onset of the Younger Dryas, North America lost approximately 70% of its large mammal species. This was not a gradual decline. It was a mass extinction event, and its speed and selectivity have puzzled scientists for generations. The animals that went extinct were almost exclusively large-bodied species, megafauna, while smaller species survived largely intact. This pattern is consistent with a catastrophic event that preferentially affected large animals, which are more vulnerable to sudden environmental changes because they have slower reproductive rates, require more food, and cannot shelter as easily from extreme conditions. The overkill hypothesis, which argues that the megafauna were hunted to extinction by Clovis people, has been the traditional alternative to catastrophic explanations. The idea is simple and compelling. Clovis hunters were extraordinarily effective. Their stone tools were designed specifically for hunting large game, and the animals they hunted had no evolutionary experience with human predators and were therefore easy targets. According to this hypothesis, the Clovis people simply hunted the megafauna faster than the animals could reproduce, driving them to extinction in a wave of destruction that moved across the continent. But the overkill hypothesis has its own problems. The timing does not perfectly match the evidence. Some megafaunal species appear to have survived well beyond the initial Clovis period, and others appear to have been in decline before Clovis hunters arrived. The number of confirmed Clovis kill sites, places where the archaeological evidence clearly shows humans killing megafauna, is surprisingly small. To put that in perspective, if the Clovis people truly hunted the mammoths to extinction, we would expect to find kill sites by the hundreds or thousands, not by the dozen. The scarcity of confirmed kill sites suggests that while the Clovis people certainly hunted mammoths and other megafauna, hunting alone was probably not sufficient to drive them to extinction. Some researchers have used computer simulations to model the overkill scenario, and while some models suggest that a small but persistent hunting pressure could theoretically drive slow-reproducing megafauna to extinction over several centuries, other models show that the populations could have sustained moderate hunting indefinitely. The debate hinges on assumptions about megafaunal population sizes, reproductive rates, and the intensity of Clovis hunting, all of which are difficult to estimate from the archaeological record. Only about a dozen for mammoths across the entire continent. And the overkill hypothesis does not easily explain why the extinctions coincide so precisely with the Younger Dryas onset, a climate catastrophe that provides a much more obvious mechanism for mass extinction. The truth may lie in a combination of factors. The megafauna may have been stressed by human hunting, weakened by habitat changes, and then pushed over the edge by the catastrophic events of the Younger Dryas onset. Whether those events were caused by a cosmic impact, a meltwater pulse, or some combination of the two, the popularization of the Younger Dryas impact hypothesis owes much to the work of Graham Hancock, a journalist and author who has devoted considerable effort to investigating the impact theory and bringing it before a popular audience. Hancock's books, including Fingerprints of the Gods and America Before, have introduced millions of readers to the possibility that a cosmic catastrophe reshaped human history. Hancock's work is controversial in academic circles. Some archaeologists and scientists dismiss him as a pseudoscientist peddling unfounded speculation. Others acknowledge that while Hancock sometimes overreaches in his interpretations or presents speculative connections as established facts, he has performed a valuable service in drawing public attention to serious scientific questions that might otherwise remain confined to technical journals. Hancock has been particularly interested in the connections between flood myths in various cultures around the world and the actual catastrophic events of the Younger Dryas. Many ancient myths, from the biblical flood narrative to the flood accounts of Mesopotamia, from the deluge myths of Mesoamerica to the flood traditions of Asian cultures, describe a catastrophic inundation that destroyed the world and required humanity to rebuild civilization. Hancock has suggested that these myths may preserve ancestral memories of the Younger Dryas catastrophe, passed down through oral traditions across generations until they were eventually recorded in written form. Whether these myths represent accurate cultural memory of a real event, or are instead universal archetypal narratives that cultures independently invent, is a matter of legitimate debate. But the global prevalence of flood myths is striking, and the possibility that they encode memories of real catastrophes deserves serious investigation. Hancock has also brought attention to certain megalithic structures around the world, including temples and stone alignments, which he suggests may have been erected in relation to astronomical events associated with the impact, or to commemorate the catastrophe. The Sphinx in Egypt has been a particular focus of his investigations, and he has developed theories about water erosion on the Sphinx's body that he claims indicates the structure is far older than conventional archaeology suggests, possibly dating back to the Younger Dryas epoch. These claims remain highly speculative and are not widely accepted by mainstream Egyptologists, but they illustrate the way the Younger Dryas impact hypothesis has captured the imagination of alternative researchers and popular authors. Now imagine once more the world as it was approaching the moment of transformation. Picture yourself standing on a high ridge in what is now Arizona, looking out across a landscape of extraordinary beauty and abundance. It is the early evening, and the sun is low on the horizon, painting the sky in shades of orange and crimson. The air is warm, and a gentle breeze carries the scent of sage and juniper. Below you, the valley stretches out to the horizon, golden grasslands interspersed with stands of pine and oak. Mammoths are grazing in the distance, vast shapes moving slowly through the grass, their tusks catching the last light of the setting sun. You can see the dust raised by their movements, and you can hear, faintly, the low rumbling calls of the herd. The camp is perhaps a kilometre away, where smoke rises from the evening fires. Hunters are returning from the day's work carrying the meat they have killed. Women are preparing food, tending the fires, working on tools and hides. Children play in the dust, chasing each other, learning through play the skills they will need. The world is vast and alive, teeming with animals, full of abundance. Tomorrow, and in all the tomorrows you can imagine, the world will continue like this. The mammoths will graze, the hunters will hunt, the women will gather, the children will play, and the seasons will turn with the regularity of a heartbeat. Winter will come, but never too harsh, never lasting too long. Summer will arrive with warmth and plenty. Life is good, and the future stretches ahead like an infinite road. The Clovis people cannot imagine that their world is about to end. They cannot imagine that the cosmic threat already exists, somewhere in the solar system, already moving along an orbit that will eventually intersect with the Earth. But on one night, still centuries away, the sky will light up with a brightness that no living person has ever seen, and in that moment, from which there is no return, everything will change. The world that emerged from the Younger Dryas was profoundly different from the world that had existed before. The great megafauna were gone, and the ecosystems they had shaped for millions of years were transformed. The Clovis culture was gone, replaced by a mosaic of smaller, more localized cultures that developed different tool technologies and different survival strategies. The climate stabilized eventually around 11,700 years ago, when temperatures rose rapidly and the Younger Dryas ended as abruptly as it had begun. And it was in the centuries immediately following the end of the Younger Dryas that one of the most important developments in human history occurred. In the Fertile Crescent of the Middle East, in the Yangtze River Valley of China, and in several other locations around the world, human beings independently invented agriculture. They began to domesticate plants and animals to settle in permanent villages and to build the foundations of what would eventually become civilization. The timing is almost certainly not coincidental. The stable, warm climate that followed the Younger Dryas provided the conditions necessary for agriculture to succeed, and the trauma of the Younger Dryas itself, the memory of a world that had suddenly turned hostile and unpredictable, may have provided the motivation. People who had lived through a catastrophe, or whose grandparents had lived through one, may have been driven to find ways to secure their food supply that did not depend on the unpredictable movements of wild animals. The earliest experiments with plant cultivation appear in the archaeological record almost immediately after the Younger Dryas ended, as if people who had survived the catastrophe were determined to never again be at the mercy of wild food sources that could disappear without warning. In the Fertile Crescent, the first domesticated wheat and barley appear around 11,500 years ago, shortly after the return of warm conditions. In China, rice cultivation began at roughly the same time. In Mesoamerica, the first experiments with maize domestication followed a similar timeline. The independent emergence of agriculture in multiple locations around the world, all within a few centuries of the end of the Younger Dryas, is one of the most striking coincidences in human history, and many researchers now believe it was not coincidence at all, but a response to a shared trauma. The people who invented agriculture were the grandchildren and great-grandchildren of the people who had survived the worst climate catastrophe in human memory, and the impulse to cultivate, to store, to plan ahead, to never again be vulnerable to the whims of nature, was burned into their cultural DNA by the experience of the Younger Dryas. The Younger Dryas was not destined to last forever. It was, despite its severity and the terror it must have inflicted on those who lived through it, a transient event, a temporary disruption in the gradually warming trajectory of the deglaciation. Around 11,600 years ago, roughly 1,200 years after the onset, the climate system suddenly shifted again. This time, the shift was in the opposite direction, away from cold and toward warmth. Temperatures in the northern hemisphere rose rapidly, not uniformly, but in a series of surges over a period of a few decades to a few centuries. The warming at the end of the Younger Dryas was nearly as abrupt as the cooling at the beginning. In the language of the ice cores, the oxygen isotope ratios shift again, this time toward higher values indicating warmer conditions. The shift happens over a period of years or decades, not centuries. The change is visible in the cores as a clear boundary, marking the end of the Younger Dryas and the beginning of what climatologists call the Holocene, the warm epoch that has continued until the present day. The causes of the end of the Younger Dryas remain debated, but many researchers suggest that the same mechanisms that triggered the collapse of the ocean circulation at the beginning of the event played a role in its termination. The reorganization of the ocean circulation, the melting of ice sheets, the atmospheric circulation patterns that had become established during the Younger Dryas period, all changed, perhaps due to orbital variations in Earth's climate forcing or due to internal variability within the climate system itself. Once the warming began, it fed on itself. As temperatures rose, more ice melted, releasing more fresh water, which over time diluted the ocean water and allowed the Atlantic meridional overturning circulation to restart. The restart of the ocean conveyor brought warm water northward again, amplifying the warming. The forest that had been restricted to small refugia during the Younger Dryas expanded rapidly, colonizing the newly habitable landscapes. The animals that had survived in restricted ranges spread northward and westward, recolonizing landscapes they had abandoned, and the human populations that had contracted to the most favorable locations began, slowly, to expand again. Now, it was in this post-Younger Dryas world, in this time of expanding forests and recovering animal populations, that one of the most important inventions in human history emerged. Pottery, the ability to create vessels from clay that could be hardened by fire, appears in the archaeological record around 9,500 to 11,000 years ago, very shortly after the end of the Younger Dryas. The earliest pottery appears almost simultaneously in multiple parts of the world, in Japan, in the Middle East, in Africa, and in other regions, a global phenomenon that emerged within a few centuries of the end of the Cold Period. The invention of pottery was transformative. It allowed liquids to be stored and transported. It allowed the rendering of fats and oils, which could then be used for cooking, lighting, and other purposes. It allowed the cooking of foods in ways that had not been possible before, by boiling rather than just roasting. The invention of pottery appears to correlate closely with the invention of agriculture. Settled agricultural societies needed ways to store grain and other foodstuffs. They needed vessels for preparing food and water. Pottery provided all of this. And perhaps pottery served a symbolic function as well, representing humanity's ability to transform raw materials from the earth into useful objects, a metaphor for the transformation of the wild landscape into cultivated farmland. The period immediately following the end of the Younger Dryas was not characterized by stable, permanent warmth. Instead, there were several additional climate oscillations, smaller than the Younger Dryas but still significant. The most notable of these is the Piora Oscillation, a cold period that occurred roughly 9,000 to 8,300 years ago, a return to near Younger Dryas conditions that lasted a few centuries and affected particularly the mountain regions of Europe. The Piora Oscillation appears in the ice core records as a small but distinct dip in temperature, visible in multiple cores and associated with a brief expansion of glaciers in alpine regions. The Piora Oscillation reminds us that the climate system does not settle into equilibrium easily. The end of the Younger Dryas did not immediately produce the stable climate of the modern Holocene, but rather a period of readjustment during which the climate continued to fluctuate, albeit on a smaller scale than during the Younger Dryas itself. Agriculture was, in a sense, humanity's response to the terror of the Younger Dryas, a way of asserting control over a world that had proven itself capable of terrible and sudden violence. The Younger Dryas also coincides, remarkably, with the construction of Göbekli Tepe, the oldest known monumental structure in the world, built in southeastern Turkey roughly 11,600 years ago, before agriculture, before pottery, before metalworking, before any of the things we traditionally associate with civilization. Göbekli Tepe consists of the pillars are T-shaped, standing up to 18 feet tall, and they are arranged in concentric rings within circular enclosures that were deliberately buried after use, as if the builders wanted to preserve them for some future purpose or to seal away whatever power they contained. The carvings on the pillars are extraordinary. They depict lions, bulls, foxes, scorpions, vultures, snakes, spiders, and other animals with a vividness and artistic sophistication that was not supposed to exist at this point in human history. Some of the pillars appear to have been anthropomorphic, with carved arms and hands as if they represented human figures or perhaps supernatural beings. The site was not a settlement. There are no domestic structures, no hearths for cooking, no storage facilities for grain. It appears to have been a purely ceremonial or religious centre, a place where people gathered from surrounding regions to perform rituals whose meaning we can only guess at. The fact that hunter-gatherers, people without agriculture, without pottery, without metal, built a monumental complex of this scale, and complexity has forced archaeologists to completely rethink the relationship between monumentality, religion, and social complexity. Göbekli Tepe suggests that it was not agriculture that led to religion and organised society, as had long been assumed, but rather the reverse, that religious impulse and communal ritual drove the development of settled life and ultimately agriculture. Massive stone pillars arranged in circles, some of them weighing over 10 tons, carved with intricate images of animals, many of which were going extinct or had recently gone extinct. The connection between the Younger Dryas event and much more ancient monuments remains speculative, but it deserves mention in the context of catastrophic theories. The Sphinx of Giza, that enormous limestone monument that has guarded the Giza Plateau for millennia, shows clear evidence of water erosion on its body and enclosure. This erosion is unusual in the arid climate of modern Egypt, where water is scarce and rainfall is minimal. The conventional explanation is that the erosion dates to when Egypt had a more humid climate thousands of years ago, and that the Sphinx was built during the Old Kingdom, roughly 4,500 years ago. But some researchers have suggested an alternative interpretation. If the Younger Dryas event affected Egypt with particular intensity, bringing significantly increased rainfall to the region around the Nile, then the water erosion visible on the Sphinx's body might date to that period. This would suggest that the Sphinx was already ancient at the time of the Younger Dryas, perhaps built during an earlier period of human civilization that remains mysterious and hidden beneath the sands of the Egyptian desert. These ideas about the antiquity of the Sphinx and its connection to the Younger Dryas remain deeply controversial and are largely rejected by mainstream Egyptologists, who argue that the evidence does not support such early dating. But they illustrate the way the Younger Dryas impact hypothesis has captured the imagination of researchers interested in ancient civilizations, and they remind us that mysteries about the past remain, and that some of these mysteries may eventually be resolved through a deeper understanding of the Younger Dryas event and its global implications. The psychological impact of the Younger Dryas on human consciousness must have been profound. Imagine being a member of the Natufian culture in the Levant, a culture that had recently discovered the benefits of settling in permanent villages and beginning to cultivate plants. Your village is located on the Euphrates River, a reliable source of water and a magnet for game. You have begun storing grain from wild grasses, and you have developed the earliest forms of agriculture. The future looks promising, and then, within a few decades or a few centuries, the climate turns hostile, the river becomes unpredictable, the game becomes scarce, the plants you were beginning to cultivate struggle to grow in the altered climate. The very foundations of your new settled way of life begin to crumble. Your people are forced to abandon the village and return to a nomadic lifestyle, following game herds across the increasingly difficult landscape. This experience of sudden reversal, of progress turning to catastrophe, of the ground beneath your feet becoming unreliable, must have profoundly shaped the cultural consciousness of the peoples who lived through it. Is it any wonder that in the myths and flood stories that eventually emerged from these cultures, thousands of years later, when the events themselves had become lost in the fog of the distant past, the memory persisted of a world destroyed by water and chaos? The flood myths of the ancient world are remarkably consistent in their fundamental narrative. There is a period of abundance and stability. There is a warning or a portent of doom. And then comes the catastrophe, a deluge of water that destroys the world and kills most of humanity. Only a few are saved, usually through divine intervention or through their own ingenuity and preparation. After the flood, survivors rebuild civilization. This narrative pattern appears in the Epic of Gilgamesh, one of the oldest surviving written texts in human civilization. It appears in the Bible, in the Hindu scriptures, in the mythologies of Mesoamerica, in the stories of indigenous peoples of the Pacific Northwest. The ubiquity of the flood myth across cultures separated by vast distances and with no historical connection suggests that it may be encoding a genuine memory of a catastrophic event that affected human consciousness deeply enough to be encoded in stories passed down through thousands of years. The Younger Dryas offers a mechanism by which such a memory could have been preserved, a catastrophe of sufficient magnitude to reshape the world, to kill vast numbers of people, to destroy established ways of life, would certainly leave an impression that would be retold and transmitted across generations. And once such a story entered the oral tradition, it would be shaped and elaborated by each generation, acquiring mythological elements and becoming connected to other stories and traditions. By the time the flood myths were written down thousands of years later, the original catastrophe had become faded and transformed, but the core narrative structure remained, a ghost of a real event preserved in the amber of ancient story. Some researchers have suggested that Göbekli Tepe may have been built in response to the Younger Dryas event, a monument to a catastrophe, a memorial to a lost world, or perhaps a ritual centre dedicated to preventing such a catastrophe from ever happening again. The connection between Göbekli Tepe and the Younger Dryas is speculative, but it is tantalising, and it speaks to the profound psychological impact that the event must have had on the people who lived through it. Imagine the ecological impact of the megafaunal extinction was profound and long-lasting. The large herbivores of the Pleistocene, the mammoths, mastodons, ground sloths and camels, shaped the landscape through their grazing, browsing and movement. Mammoths, in particular, were landscape engineers. Their size and strength allowed them to knock down trees, creating and maintaining grasslands that would otherwise have been forested. They trampled vegetation, creating pathways and preventing the development of dense undergrowth. Their dung fertilized the soil and dispersed seeds across vast distances. When the mammoths vanished, the landscape changed. Forests expanded into areas that had been grasslands. The open, park-like landscapes of the Ice Age, with scattered trees and vast expanses of grass, gave way to denser forests. This change in vegetation affected not just the megafauna but the entire ecosystem. The predators that had depended on the large herbivores went extinct. The megafaunal extinctions cascaded through the food web, affecting herbivores of all sizes, carnivores of all sizes, and the vegetation communities that supported them all. In the modern era, some researchers have begun to wonder whether recreating aspects of the Pleistocene ecosystem might be desirable. The rewilding movement, which advocates for restoring areas to more natural wild conditions, has sometimes drawn inspiration from the Pleistocene megafauna. Researchers and conservation biologists have suggested that reintroducing large herbivores like horses, camels and elephants to areas from which they have been absent for thousands of years might restore some of the ecological functions that the Pleistocene megafauna provided. Projects like Pleistocene Park in northeastern Siberia have begun to reintroduce large herbivores to areas of tundra and grassland, with the goal of recreating something like the mammoth steppe ecosystem that existed during the Ice Age. The question of whether we can or should recreate the Pleistocene raises profound questions about our relationship with nature. But it also reminds us of what was lost when the mammoths and other megafauna vanished. The Pleistocene was not a static state, but a dynamic ecosystem shaped by the activities of large animals and by the climate conditions that supported them. The loss of the megafauna was not merely the loss of individual species, but the loss of ecological functions that had shaped the planet for millions of years. Now, let us imagine once more the landscape in those final years before the impact. Picture yourself standing in the great grasslands of the North American Great Plains, roughly 13,000 years ago, 600 years before the Younger Dryas. The sky is enormous, stretching in every direction to the horizon, with puffy white clouds drifting slowly from west to east. The grass beneath your feet is tall, reaching to your knees or waist, and it waves in the gentle breeze like a golden sea. In the distance you can see herds of mammoths, bison, and horses, vast congregations of animals moving slowly across the landscape. The thunder of their hooves shakes the ground beneath your feet. There is no human settlement visible, no signs of people, and yet people are here, in small bands scattered across the landscape, hunting the abundant game. A campfire glows in the distance, smoke rising into the vast sky. The sound of voices carries on the wind, laughter and conversation, in a language that has been dead for over 10,000 years. The stars at night are brilliant and bright, unpolluted by artificial light, visible in their full majesty stretching across the entire sky from horizon to horizon. The Milky Way arches overhead, a river of light, The modern study of the Younger Dryas, brought to public attention by pioneering researchers like Richard Firestone, William Topping, and Alan West in the early 21st century, represents an effort to read the past accurately and to learn its lessons. The impact hypothesis was radical and controversial when first proposed, but science is a process of questioning and testing and refining our understanding. As new evidence accumulates, as new dating techniques are developed, as new research methods allow us to examine the ancient record with unprecedented detail, our understanding of the Younger Dryas has evolved. What began as a speculative hypothesis has become increasingly plausible, and the scientific conversation has shifted from whether a cosmic event occurred to the nature and magnitude of that event, and the exact mechanisms through which it triggered global climate change. The discovery of the Hiawatha crater in Greenland, while still debated in terms of its age and origin, represents a crucial piece of evidence that large impacts can be hidden beneath ice sheets, exactly as the impact hypothesis predicted. The accumulation of platinum anomalies in multiple ice cores from independent research groups demonstrates that the signal is real and reproducible, not an artifact of methodology or contamination. The consistent appearance of shocked quartz, nanodiamonds, and other impact markers at sites around the world, all occupying the same stratigraphic position, tells a story of global catastrophe that cannot be easily dismissed. The psychological and cultural impact of the Younger Dryas on human consciousness likely persists even in the modern age. The myths and stories that encoded memories of the event, transmitted across generations through oral traditions and eventually written down in sacred texts and legends, shaped the religious and philosophical worldviews of the cultures that produced them. The Younger Dryas appears in the Bible, in Hindu scripture, in the traditions of indigenous peoples. The question of whether these myths accurately represent a real historical event, or whether they are universal archetypal narratives that different cultures independently developed, may never be conclusively answered. But the possibility that they preserve some memory of the catastrophe is intriguing and worth serious investigation. As we face our own era of uncertainty and change, with environmental challenges and technological disruptions transforming the world at an accelerating pace, the story of the Younger Dryas offers perspective. Our ancestors survived the worst catastrophe that nature could throw at them, not through superior technology, but through adaptability, ingenuity, and the social bonds that held their communities together. The trauma of the event likely impelled them to invent agriculture, to develop new technologies, and to create the foundations of civilization. We can learn from their example, recognizing that catastrophe need not be the end of humanity, that adaptation and innovation are possible, and that the social bonds that connect us to each other may be among our most valuable resources in times of crisis. And somewhere out there, in the darkness between the stars, an object is moving along its eternal path through space, already targeted for a collision with Earth, still centuries away but absolutely inevitable. The Clovis hunters of this landscape cannot see it. They cannot sense it. They have no way of knowing that their world is about to end. They look up at the stars as humans have always done, reading stories in the constellations, finding navigation and meaning in the heavens. The sky seems eternal and unchanging, a backdrop to the eternal drama of hunting, gathering, surviving, and thriving in a world of spectacular abundance. But the sky contains the seeds of catastrophe. The peace of this moment, this interlude of warmth and plenty, is about to be shattered in ways that cannot be imagined by those living through it. Watching the world you knew collapse around you, some of the most haunting evidence for the suddenness of the Younger Dryas comes from frozen mammoth carcasses found in Siberia and Alaska. Several of these carcasses show signs of extremely rapid death and freezing, with undigested food still in their stomachs and mouths, as if the animals were killed and frozen so quickly that the normal processes of decay did not have time to begin. The famous Beresovka mammoth, found in Siberia in 1900, in 2007, a reindeer herder in Siberia discovered the most perfectly preserved baby mammoth ever found, a female calf named Lyuba who died approximately 41,000 years ago. Her skin, hair, and internal organs were intact. While Lyuba predates the Younger Dryas, her preservation illustrates the extraordinary power of permafrost to freeze organic material almost indefinitely. The famous Beresovka mammoth, found in Siberia in 1900, had buttercups and other summer plants in its mouth and stomach, suggesting that it died during the warm season and was frozen almost immediately. While some of these frozen carcasses predate the Younger Dryas, Others date to roughly the right time period, and they suggest a world in which catastrophic cold could arrive with almost no warning, freezing the landscape and everything in it in a matter of hours or days, watching the great animals disappear one by one, watching the climate turn hostile, watching your people struggle and die. And then imagine trying to make sense of it, trying to understand why the world had punished you, and trying to find a way to appease whatever forces had caused such destruction. Göbekli Tepe may be the physical expression of that trauma, carved in stone by people who wanted to ensure that the memory of the catastrophe would never be forgotten. The story of the Younger Dryas is not merely a story about the past, it is a warning about the fragility of the world we live in. The climate system is not a gentle, predictable machine. It is capable of sudden, violent shifts that can transform the entire planet in the span of a single human lifetime. The ocean circulation patterns that keep our current climate stable are the same patterns that shut down 12,800 years ago, and scientists today are watching with growing concern as the Greenland ice sheet melts at an accelerating rate. The Greenland ice sheet contains enough frozen water to raise global sea levels by over 7 meters if it were to melt completely, and the rate of melting has accelerated dramatically in recent decades. In 2019 alone, Greenland lost over 500 billion tons of ice, more than at any time in recorded history, and the meltwater is flowing into the very same region of the North Atlantic that received the catastrophic freshwater pulse 12,800 years ago. Recent studies have shown that the AMOC has already weakened by approximately 15% compared to the mid-20th century, and some climate models predict that continued greenhouse gas emissions could push the system past a tipping point beyond which the conveyor belt could shut down entirely. A full AMOC shutdown in the modern world would have consequences that are difficult to overstate. Northern Europe could see average temperatures drop by 5 to 10 degrees Celsius within a few decades, making agriculture in much of Scandinavia and the British Isles extremely difficult. Rainfall patterns would shift dramatically across the tropics, potentially devastating food production in regions that support billions of people. Sea levels would rise disproportionately along the eastern coast of North America due to changes in ocean circulation. The Younger Dryas is not just ancient history, it is a template for what could happen again, and the mechanisms that triggered it are disturbingly similar to the processes that are unfolding right now. Pouring fresh water into the North Atlantic in a pattern that eerily echoes the conditions that preceded the Younger Dryas. In the context of understanding cosmic threats to our world, we must acknowledge that the solar system is a far more dynamic and dangerous place than was commonly appreciated in the 20th century. The discovery of near-Earth asteroids has accelerated dramatically in recent decades, driven by improved telescopes, dedicated survey missions, and computational methods for tracking and predicting orbits. When NASA's Planetary Defense Coordination Office began systematically cataloguing near-Earth objects, they discovered that the number of potentially hazardous asteroids is far larger than previously believed. The challenge is that smaller objects, the type most likely to strike Earth, are harder to detect and track than large objects, and many may remain undiscovered until they are already on a collision course with Earth. The Chelyabinsk event of 2013 demonstrated how quickly an object can arrive without warning and how dramatic its effects can be. The object was estimated to be about 20 meters in diameter, and it approached the Earth from the direction of the Sun, making it nearly impossible to detect from Earth-based observatories. It exploded over Russia with a force of 500 kilotons of TNT, an explosion equivalent to the combined yield of the nuclear bombs dropped on Hiroshima and Nagasaki. It caused injuries to over 1,500 people, flattened trees over a wide area, and generated an economic loss estimated at billions of rubles. And yet, it was a relatively small object compared to what might have triggered the Younger Dryas. The question is not whether a large object will strike Earth, but when. The geological record makes clear that impacts are inevitable over sufficiently long timescales. The question is whether our species will have the technological sophistication to detect such an object and alter its trajectory, or whether humanity will instead experience first-hand the catastrophe that befell the Clovis people over 12,000 years ago. The modern climate crisis presents another threat, one that operates through different mechanisms than a cosmic impact, but one that similarly has the potential to trigger rapid climate changes. The melting of the Greenland ice sheet and the disruption of the Atlantic meridional overturning circulation are concerns that climate scientists are monitoring closely. Some models suggest that the AMOC could weaken or collapse if freshwater input from melting ice reaches critical thresholds. While the melting is occurring gradually compared to the catastrophic flood that may have preceded the Younger Dryas, the endpoint could be similar, a disruption of the ocean conveyor belt that could trigger cooling in the northern hemisphere and disruption of rainfall patterns around the globe. The Younger Dryas event reminds us that our climate is capable of dramatic shifts, and that the systems we depend on are more fragile than the long period of stability that has characterized the Holocene might suggest. The invention of agriculture occurred in response to climate instability and catastrophe. The rise of civilization is founded on the assumption of climate stability. The vast agricultural systems that feed billions of people depend on consistent rainfall patterns and stable growing seasons. A sudden disruption to these patterns, whether from a cosmic impact from volcanic activity or from human-induced climate change, could have cascading consequences that would rapidly become catastrophic. The Younger Dryas serves as a warning from the deep past, a reminder of what is possible, and a lesson in humility about the fragility of the world we inhabit. The story of the Younger Dryas is thus not just ancient history, divorced from the modern world. It is a story that speaks directly to the present moment, to our own era of rapid change and global challenges. The mechanisms that operated 12,800 years ago are not locked in the past, irrelevant to the future. The climate system can shift rapidly. The ocean circulation can collapse. Cosmic threats are real and present, and humanity, despite all of our technological sophistication, remains vulnerable to forces that can reshape the world in timescales shorter than the human lifespan. The Younger Dryas event ended, as we have discussed, in a return to warmth and the establishment of stable conditions. But it took over 1,000 years of suffering and survival for that end to arrive. The question for our time is whether we will develop the wisdom and foresight to prevent catastrophes rather than merely surviving them after the fact. We are not immune to the forces that shape the past. The cosmic threat is also real. The solar system is full of debris, comets and asteroids and fragments of shattered worlds, and the Earth has been struck many times in its history. The object that may have triggered the Younger Dryas was not particularly large by cosmic standards, perhaps only a few kilometers across, and NASA's Planetary Defense Program has catalogued more than 32,000 near-Earth objects. But scientists estimate that there are many more that remain undiscovered, particularly among the smaller objects that are harder to detect, but still capable of causing regional or continental devastation. The Chelyabinsk meteor that exploded over Russia in 2013 was only about 20 meters in diameter, and its airburst released energy equivalent to 500 kilotons of TNT, injuring over 1,500 people and damaging thousands of buildings. The object that may have triggered the Younger Dryas was perhaps 200 times larger. The Chicxulub impactor that killed the dinosaurs 66 million years ago was roughly 10 kilometers across, but the Younger Dryas impactor, if it existed, was far smaller and still managed to reshape the entire planet. The solar system is not the orderly, predictable place we like to imagine. It is a shooting gallery, and Earth moves through it every day. Objects of that size pass near the Earth with disturbing regularity. The question is not whether the Earth will be struck again, but when and whether we will be prepared. The exact mechanism by which a cometary impact would have vaporized the Laurentide ice sheet deserves deeper exploration. When an object traveling at a velocity of tens of kilometers per second strikes a surface, the energy is released not gradually but instantaneously in the impact zone. The pressure exceeds millions of atmospheres, and the temperature rises to thousands or tens of thousands of degrees Celsius. Under such conditions, rock and ice do not behave as they do under normal conditions. Rock does not shatter slowly but rather vaporizes. Ice does not melt in the ordinary sense, but sublimes directly from solid to gas, bypassing the liquid phase entirely. If an object measuring several kilometers across struck the Laurentide ice sheet, the resulting crater would have been enormous, perhaps hundreds of kilometers in diameter. But the crater would not have persisted. The heat of the impact would have vaporized ice and rock across an enormous area, creating a cavity that would almost immediately begin to collapse as the surrounding ice flowed inward. The surrounding ice, still intact and under the pressure of the weight of overlying ice, would flow toward the impact site like water flowing toward a drain. Within hours or days, the surface expression of the impact would be completely erased, hidden beneath the flowing ice, invisible to the eye. But the effects would persist. The impact would have disrupted the stability of the ice sheet. The heat would have penetrated deep into the ice, lubricating it, causing it to flow more rapidly. The meltwater would have accumulated beneath the ice sheet, in subglacial lakes that are invisible from above but which exist in the modern ice sheets of Greenland and Antarctica, and the shock of the impact would have propagated through the ice and into the underlying bedrock, potentially triggering earthquakes and landslides. The largest consequence would have been the release of the freshwater lakes dammed by the ice sheet, the catastrophic floods that would have carried icebergs and sediment across the continent. But there would have been other consequences as well. The atmospheric effects alone would have been devastating. The vaporized ice and rock ejected into the upper atmosphere would have created a pall that would have lasted for weeks or months. The soot from the ignited wildfires would have added to the atmospheric opacity. The result would have been a period of rapid cooling, analogous to the nuclear winter scenario, but triggered by cosmic catastrophe rather than human war. The cooling would have been severe enough to trigger agricultural collapse in any civilization that existed at the time, which fortunately for humanity, the Clovis culture had not yet developed. But the climate effects would have extended far beyond North America. The disruption of the ocean circulation caused by the freshwater influx would have altered rainfall patterns globally. The monsoons that depend on ocean circulation patterns would have weakened or shifted. The intertropical convergence zone, the band of rainfall that circles the equator, would have shifted, bringing drought to some regions and flooding to others. Imagine the perspective of human beings living in Africa during the Younger Dryas, or in Asia. They would not have known of the impact in North America. They would not have understood the cascade of causes and effects that were transforming their climate. They would simply have experienced the effects, the droughts in some regions, the flooding in others, the changes in animal populations, the failures of crops and game. They would have attributed these changes to the actions of gods, to violations of natural law, to the anger of the spirits that inhabited the world. In their oral traditions and eventually in their written myths, they would have described the catastrophe in terms that made sense in the context of their own worldview. And so the Younger Dryas spread around the world not as a single event perceived from a single location, but as a global climate disruption felt differently in different places, yet clearly caused by something that affected the entire planet simultaneously. Now imagine yourself, a person of the time, someone living through the earliest years of the Younger Dryas event in what is now the Middle East. The spring has been cold, and the growing season was short. The wild wheat and barley that you and your group have been gathering have not grown as abundantly as in previous years. The rivers, normally reliable sources of water and fish, have become erratic, sometimes flooded and dangerous, sometimes low and restricted. The gazelles that your hunters pursue have begun to move, following the shifts in vegetation. Some are moving south toward the desert, as if they know something you do not know, as if they sense the catastrophe coming. Your people are growing anxious. The foods that sustained you through the previous generations are becoming scarce. The social structures that bound your group together are being strained as you all struggle to find enough to eat. You are hearing stories from traders and travellers who come to your settlement from distant lands. They tell of ice advancing in the north. They tell of vast cold that has gripped lands that were warm. They tell of peoples abandoning settlements and moving south driven by cold and hunger. The world you know is changing, and you feel powerless to stop it. You perform rituals and ceremonies, trying to appease the spirits or the gods that you believe control the weather. You gather more intensely, working longer hours to bring in enough food. You hunt with greater desperation, killing animals that you previously spared, knowing that survival depends on acquiring as much meat as possible before winter comes. And winter, when it comes, is longer and harsher than it should be. The cold extends into spring and early summer. The frost kills the plants that you're trying to cultivate. The herds of gazelle and other game continue to move south and west, following food sources. Some of your people sicken. Some die. The very old, the very young, and the weakest among you die first, as they always do in times of scarcity. But even the strong and the healthy are weakening from insufficient food and constant cold. And you wonder, as humans always wonder in times of crisis, whether the world will ever return to normal, whether the abundance you once knew will ever come again, whether your people will survive to see warm days and plenty once more. This is the lived experience of the Younger Dryas, not the abstract climatic and cosmic mechanisms of impact and ocean circulation disruption, but the human experience of catastrophe and survival, of loss and adaptation, of societies being tested to their limits, and either surviving or disappearing into the archaeological record, leaving only faint traces behind. The Younger Dryas teaches us that catastrophe can come swiftly, without warning, and that even the most successful and well-adapted cultures can be swept away in the span of a generation. The Clovis people were the apex predators of their continent, the most technologically sophisticated culture in the Western Hemisphere, and they disappeared so completely that we did not even know they existed until their spear points were found at a site near Clovis, New Mexico, in 1929. If it happened to them, it can happen to us. The story of the Younger Dryas can be read at multiple scales, from the global mechanisms of climate change and ocean circulation to the intimate details of human survival and adaptation. At the broader scale, the Younger Dryas reveals the interconnectedness of the Earth system. An event that occurs in the atmosphere above North America has consequences that ripple through the ocean circulation, affecting climates thousands of kilometers away. The disruption of rainfall patterns in one region affects the availability of food in other regions. The extinction of animals in one continent affects the ecological balance in distant lands. The Earth is one system, and what happens in one part affects all parts. The Younger Dryas also teaches us that the systems we depend on operate within narrow ranges of tolerance. The climate, the ocean circulation, the monsoons, the rainfall patterns that support agriculture, all of these are balanced on a knife's edge. A disruption of sufficient magnitude can knock them out of balance, and once they are knocked out of balance, the return to equilibrium is not automatic but requires the passage of time, sometimes centuries or millennia. We live in a time of remarkable technological achievement and material abundance. We have developed medicines that cure diseases that once killed millions. We have created technologies that connect us across the globe. We have built cities and civilizations that stretch across continents. We have cultivated crops and domesticated animals in ways that would have seemed miraculous to our ancestors. And yet, we remain vulnerable to forces that operate at a scale larger than ourselves, forces that we cannot always control or predict. The Younger Dryas is a reminder of this vulnerability. It is a mirror held up to our own time, reflecting back the fragility of the systems we depend on and the impermanence of the world we take for granted. The people of the Clovis culture could not have imagined that their world was about to end. They lived in a time of apparent plenty and stability, with no warning of what was coming, but the warning signs existed, hidden in the solar system, in the cosmos beyond Earth, in the physics of objects moving along orbital trajectories. We, in our own time, have the advantage of knowledge. We can observe the sky with telescopes and computers. We can track near-Earth asteroids. We can model climate systems and predict their responses to disruptions. We can read the past in ice cores and sediment layers and fossils. And yet, having this knowledge, what do we do with it? Do we heed the lessons of the past and take steps to prevent catastrophe? Or do we continue on our current trajectory, assuming that the future will resemble the recent past, that the systems we depend on are more stable and more forgiving than the Younger Dryas suggests? These are not questions that can be answered in this script. They are questions that each person must answer for themselves, in the context of their own life and their own choices. But the Younger Dryas reminds us that such questions matter, that the choices we make in the present have consequences that extend far into the future, and that the world is more fragile and more dynamic than we often assume. The megafauna are gone. The Clovis spear points lie buried in the earth. The glaciers that advanced during the Younger Dryas have retreated again, leaving behind a landscape of lakes and moraines and erratics that tell the story of ice to anyone who knows how to read them. But the story itself is written in the very bones of the earth, in the black mat that lies hidden beneath our feet, in the nanodiamonds and microspherules and charcoal layers that mark the moment when the world changed. And somewhere out there, in the darkness between the stars, there may be another object on a path that will one day intersect with ours, carrying the potential to reset the world once again. In conclusion, the Younger Dryas stands as one of the most significant events in human history, a moment when the world was transformed by forces beyond human control, and when human beings were tested and challenged to adapt, survive, and eventually to thrive. The impact hypothesis, controversial as it remains, provides a compelling explanation for this event, an explanation that draws on evidence from physics, chemistry, geology, and astronomy. Whether or not the impact hypothesis proves to be entirely correct in all its details The evidence for some kind of catastrophic event at the Younger Dryas boundary is compelling and worth serious scientific investigation. But that is a worry for another night. Tonight, let the story settle over you like snowfall, gentle and quiet and slow. Let the mammoths walk through your dreams, enormous and peaceful and unaware of what is coming. Let the Clovis hunters crouch by their fires, shaping their beautiful spear points by the light of a sky full of stars, a sky that may have held, on one fateful night, a light brighter than any they had ever seen. And let that light fade, as all lights do, into the long darkness of sleep.